This year, 2016, Tokamak Energy is beginning construction of its new machine, ST40. ST40 is a spherical tokamak design, so it's a more squashed up, compact shape, and it has a very high magnetic field for its size, about 3 Tesla, which is about the same as the jet tokamak at Cullum. ST40 will stand 4 meters tall, 2.5 meters wide, and it will have a plasma volume of a cubic meter. The main aims of ST40 are
to achieve 100 million degrees,
to test the technique of merging compression to start up and heat the plasma,
to see how the plasma behaves in a high-field compact machine.
Attaining 100 million degrees, that is fusion temperatures, in a small tokamak will be an exciting step forward for Tokamak Energy. ST40 will use copper magnets cooled to liquid nitrogen temperatures, that's about minus 196 degrees C. Future machines will use high-temperature superconducting magnets, which are currently under development. But you might be wondering, what are the main elements of ST40, and how do they come together to form the whole tokamak? This is the center column. It fits down the middle of the machine, and it actually has 2 parts: the central wedges of the toroidal field magnets and a large solenoid. The solenoid maintains a current flowing through the plasma, which is important for plasma stability. But the toroidal field magnets generate the magnetic field that keeps the plasma confined. They come together as follows. Inside the solenoid there are 24 wedges that fit together. These form part of the big toroidal field magnets that loop around the donut vessel. There are 8 sets of 3 limbs that are bolted together and electrically insulated that connect to the wedges in the center column and form the toroidal field coils. Grouping the limbs together makes it easier to access the plasma through the gaps. The orange pieces here are strengthening. The high magnetic fields and high currents can generate large forces on the machine. Outside the center column is the inner wall of the inner vacuum chamber. The rest of the inner vacuum chamber builds out around it to form a hollow ring. The plasma will be within this ring. These are all the poloidal magnetic coils, shown here with the center column. These are the coils that make magnetic fields that are used for shaping and controlling the plasma. Let's look at them separately. These are the diverter coils. They shape the magnetic field so that excess heat and particles are diverted to a strengthened area of the machine where they can be removed. The merging compression coils will be used to start up the plasma by creating the plasma current that the solenoid will then sustain. Merging compression is where the energy will come from to achieve the 100 million degree temperatures. These are the vertical field coils, upper, medium and lower. They provide an inward force to control the size of the plasma ring. And finally, these are the Super X coils. They are part of the diverter, and they allow us to drag the diverted particles out over a larger area to reduce the heat on the wall. Outside these magnetic coils is the outer vacuum chamber. Along with the inner vacuum chamber walls, this forms the cryostat. The cryostat keeps the coils at liquid nitrogen temperatures. The copper conducts much better when it is cold, and so it increases the magnetic field created. So those are all the important components of ST40. Here's how they'll be assembled. The inner vacuum chamber with the merging compression and diverter coils. The center column and solenoid that slots down the middle. Next come the return limbs and their supports, followed by the outer vacuum chamber and the remaining vertical field coils. This will be ST40, the world's first compact high-field tokamak.